Hello, this is the overview video for the hierarchical controller for surveillance, automatic surveillance that we have developed at the Institute of Automatic Control in ETH Zurich. So I'll run you through these graphs. There are some more videos where the performance of the system is shown, but in this first one we go through each of these graphs independently and explain what the results are. So just a small introduction to the project. What we're doing here is we're using some robotic evaders, and these are placed on a table in one of the laboratory rooms that we have. And on this table, these robots move randomly or moved by a certain user, but their movement is governed by a certain model that we have also estimated for the purpose of this project. And according to this model, we kind of project what these targets will do in the future, so how they move in space, and use that to try and maximize the probability of capturing them with movable cameras. So on the top of the ceiling of this room, actually on the wall of this room, there are two pan tilt cameras, which means that they can move around their field of view. And with them, we're trying to figure out the optimal control inputs such that we capture the objects, or we maximize the probability of capturing them or tracking them. And that's the main purpose of this project, that we have different objectives. The objectives are described mathematically with the framework of stochastic reachability. And this is explained in our publications, where links are provided in the channel. And yeah, we use this mathematical framework to kind of get a proper get an idea of what the probability of successfully achieving these different objectives is. The reason why the objectives of tracking, acquiring, and others is described by probability is that the movement of the robotic evaders is stochastic. Okay, and that is depicted in the model of movement of these robots, and this is used by the cameras to solve the stochastic reachability objectives, as we call them, which are essentially the objectives of tracking or acquiring the objects moving in their space of surveillance. These objectives are calculated in real time, actually in a sampling time of 4 Hz actually, and they're depicted in this graph on the top left corner of the image with these bars. Okay, each bar corresponds to a certain objective, and they are placed and shown for each one of the two cameras. So there's the camera at the door and there's the camera at the window. Okay, and that's because they're closer to the door and the window in our lab. One of them is red in the field of view, and the other one is blue. This is actually the bottom left picture is their projection. Okay, the green dots are the robotic evaders, which are also shown on the right side of the screen as the paper that we use to detect them. This view on the right is from the cameras, the pan tilt cameras, their zoomed in view of the real world. Also, what the red and blue areas on the left are showing. And the estimates of the robots is given by a global eye, as we call it, a camera that is placed on the ceiling of the room, and it's just statically giving us some rough estimate of where the object is, such that we can formulate the stochastic reachability objectives. This graph in the middle with the scroll bars is showing the mechanism by which the hierarchical controller makes decisions. Okay, it's basically a weighting, okay, a reward factor on the state that the system will be driven if certain objectives, certain reachability objectives are solved and achieved. Okay, so on the first bar corresponds to the reward of tracking one robot. On the second bar, the reward of tracking the other, while on the third bar, the reward of tracking both of them at the same time. Okay, and the user, whoever is the operator of this automatic surveillance system, can choose what the best thing is and accordingly form these weights. And the whole purpose of this demonstration is to show how these weights affect the performance and how effectively the hierarchical controller is deciding to allocate tasks among the cameras. If you notice now, the bars on the top left, the probabilities, the stochastic reachability objectives changed because I switched the orientation of the robot that is not in the field of view at the moment, not in the field of view of the camera at the window, which sees the other robot. And by changing the orientation, basically the projection of how the model will behave changes. And as a result, the probabilities of acquiring this other object by the camera at the window change, and that's why the bars are different. Now this changed the position of the evader. The fact that I moved the paper a bit towards the camera at the door brought it within the vicinity of the camera at the door, which means that the probability of acquiring it by the camera at the door is non-zero anymore, as you can see by the bars. And the camera decided to move and acquire it, and that's what you saw in the video. And now even the probability of tracking it, which means that capturing it, keeping the field of view on it for the whole horizon is high. The pie chart, as well as the state trajectory, which is on top of it, okay, the red line graph, are showing how the system has been performing over the time that it's on. Okay, so the pie chart, basically each color of the pie chart corresponds to a state. For example, at this situation, the blue one corresponds to seeing one robot, and that's because, and the reason why it's so big, the blue piece, is because the system has been looking at this one robot, one of the two evaders. The red one is the situation where nothing is seen, okay, none of the two robots. And the green one, the situation where both of them are seen. And the reason why there is some values here, why these are big, is that when I started recording this video, and for the purpose of this overview of the system, both of them are shown or none, and according to how you initialize the system and when you start recording, of course this pie chart is different. Okay, and this is actually a useful thing to view over long times after you've run the system for above, I don't know, for some time which is enough for you to evaluate the performance. Then this pie chart would be actually accurate and not biased according to how you started the system in the first 5 minutes, let's say. A better way to look at it is probably the trajectory of the state, where you see what the current state is with this line and how it has been changing over the past time steps. A final remark I would like to make is that there is a certain misalignment between the measurements that you get from the global eye, the camera that's placed on the ceiling, and the projection of the field of view of the movable cameras. Okay, this is not affecting the performance of the system that much, but you might notice at some points that where the robot seems to be inside the field of view of one of the movable cameras, and where it actually is when you look at the picture of that, not the projection on the table, but the picture on the right, is a bit off. But that's just a couple of centimeters, if at all. Which is not affecting the performance of the system. Hopefully this short introduction was enough to explain what the graphs are showing and provide the necessary information to follow the performance of the system in the following videos. Thank you for listening.